So we need to construct a charmed element for the quantum group. And before I can do that, I need to introduce a definition which is very classical in Lie theory, but hasn't shown up in this lecture so far. Rho is the notation of a particular element of a particular positive weight, and is defined by the property that it satisfies 2 rho paired with alpha I equals alpha I paired with alpha I. Alpha I are the simple roots. Let me give you an example of how this happens. I'll do it in type B2. This is the root system. I've drawn all the roots. And let me say that this is one of the simple roots, and that's the other simple root. So what I'm saying is, well, draw a perpendicular onto that vector. And draw a perpendicular onto that vector. And where they meet, that's this element rho. That's what this equation means geometrically. You can also think of it if you draw the cone consisting of all positive weights. That's lambda plus. Let me draw some of these weights. That's 2 rho. And there's rho, which is here in the middle. Rho is the first weight that's completely in the interior of that cone. All the other ones are on the walls. So let's write a 2 rho as a sum, as a linear combination of simple weights, of simple roots. So in this particular case, we would have here 2 rho equals, if I call this one alpha 1 and that one alpha 2, let me draw some of the things on the lattice. Here's one weight, here's a weight, there's a weight, that's also a weight, here's a weight. Here it goes. So how do I write this one as a linear combination of this orange and that orange vector? Well, it turns out to be equal to 4 alpha 1 plus 3 alpha 2. That's in this example. And then using those numbers, I can define the charmed element as being mu is the product of the ki's to the ni, where ni are these numbers. So in this particular example, we would have mu equals k1 to the 4th times k2 to the 3rd. We need to check that this element satisfies all these properties that I listed before. So we have, for example, s squared of a equals mu inverse, or delta of mu equals mu tensor mu, and similarly, s of mu equals mu inverse. These are easy to check. If you just try to check them, the second and third one are completely immediate. And the first one, if you say, I want mu to be of that form, to be some monomial in the ki's, then this first equation forces you to take it to be exactly that monomial. The other monomials just, you end up encountering this condition. So these are easy. What I want to concentrate on is the last equation, which is that one. I only gave you the formula for the R matrix for SL2, which, by the way, is written here. It's written 3 times. This is the same thing. There's no difference between those lines. And therefore, I'll check that equation in the case of SL2. In the case of SL2, then mu is simply equal to k. Kind of obvious. If you have here just one equation, then you put the coefficient 1. Okay, so what do we need to check? This equation here, so we take R, which I redraw here, and we put a mu inverse in the middle and then multiply. So what this means is that we remove this tensor product symbol and put K inverse. That's the left-hand side. What's the right-hand side? On the right-hand side, first we need to take R bar instead of R. So that's also easy. Remove this thing and put it there. That's R bar. And now we put a mu in the middle. So that's K. Okay. So these two things are the things that we need to check are equal. These elements, by the way, let's remember, they correspond to this and to that. And they were morphisms from x to x, where x is some module. And in order to be a morphism from x to x, you need to be in the center of the algebra. So these are central elements inside this Hopf algebra. And to check that two central elements are the same, we need to, what does a central element do? A central element will act as a number, as a scalar on each irreducible representation. And here, let's say that I take Q to be generic so that the representations are all irreducible. All the representations care about are irreducible. So these things really act as numbers on each irreducible representations, and to check that they're the same, we need to check that these numbers are equal in each irreducible representation. Actually, there's a little caveat. It doesn't really mean that imply that they're the same. I mean, it's conceivable that you have two elements of the center that act in the same way on all those modules that I care about. But because in the category of modules that we're looking at, we only care about those modules. For all practical purposes, they are the same element. And actually, if you want to set up things so that really what you're checking is that they're the same, you need to put an extra relation to say that if two elements happen to act in the same way on every representation, then identify them. So we're going to check that they act the same way on each irreducible module. So now we fix a module. Weyl module with highest weight lambda. And again, I'm in the SL2 case. And so let's call the highest weight vector let's call that V lambda. I've already used that notation before. And let's also introduce a notation for the lowest weight vector. And let's call it V sub minus lambda. So if I take a random vector and I try to apply this expression to it, it's very difficult. But if my vector happens to be a lowest weight vector, if I let it act on this guy, here I start with an f. And so whenever m is positive, it kills it. And that automatically gets rid of one of the summations. And it simplifies a whole bunch. For example, if I try to take this expression and evaluate it, so I take that expression, and evaluate it on v sub minus lambda, this lowest weight vector, well, what you get is that you have a single sum indexed over n of, well, this thing. Hn k inverse Hn v minus lambda. So all this stuff with the m's goes away because it acts as 0 on this particular vector. And that's something you can compute. The h's and the k's commute. I mean, they're both just functions on the weight lattice. And we get this expression, sum of this, that, h, tensor h. So that acts on this particular vector as, here, continue over there. That acts as q to the 1/2 h squared, k inverse acting on v sub minus lambda. Well, h is essentially lambda, so that's just q to the 1/2 lambda squared, and k is essentially, well, is the identity function, so k inverse applied to minus lambda is lambda. So I get an extra lambda acting on this vector. Well, the second expression can be evaluated easily on the highest weight vector, and is much more difficult to evaluate on any other vector. So we evaluate it on a highest weight vector, see what we get. And we're going to see that we get the same thing. So that is sum So the difference is that I have here k instead of k inverse and v lambda instead of v minus lambda. And I end up with the same expression. Well, the same scalar shows up in front. So I knew, because the representation W lambda is irreducible, that I have to be acting by a given scalar on the whole representation. And I computed that scalar by evaluating on this vector, and I computed the other scalar by evaluating on this other vector. The scalars happen to be equal. And so I'm happy. So that does this equation. As a bonus, we learn a nice formula for the twist of a representation of UQSL2. The twist is given by that scalar on the representation W lambda. So it's a pretty explicit formula. So yeah. So theta sub W lambda is equal to that. From that computation, that's what we learn. So now that we have a charmed element, well, now that we have essentially a ribbon category, we can define the following very important concept of quantum dimension. Oh, let's see, these are easy. I can erase them. So that's a general concept. I'm no longer in the SL2 case right now. The quantum dimension of a module V is, by definition, so I have V, I have its dual there, I have its double dual, and mu is an isomorphism between the double V and the double dual, so I take that. So I read it from top to bottom. I first do co-evaluation of V, then mu tensor 1, then evaluation of V dual. And if you work a bit with the translation between this mu element and this twist, you see that you can rewrite it, if you want, as this expression. There's actually lots of ways of rewriting it. That's one of the possible ways of rewriting it. I think this requires to use the condition S of mu is mu inverse. Or maybe not. I'm not sure. It depends how you interpret that. No, sorry, I take back. Related to the quantum dimension is the notion of quantum trace of a map. Suppose F is a map from V to V, then the quantum trace of F is defined as, well, the same thing but with an F on top. So in particular, the quantum dimension is the quantum trace of the identity map from V. So here I have V again, and here I have V double dual. I can take the quantum trace of a map from something to itself. And again, if I want, I can rewrite it in that form. And the main property that justifies its name is that quantum trace of Fg is equal to quantum trace of GF. So now F is a map from V to W, G is a map from W to V, and then here I take the quantum trace in V, or sorry, in W, and here I take it in V. This is proven very quickly, so let me just do it. So I have F, G, I use that. Okay, let me straighten it a bit. F, G, becomes like that. Then I can, this twist here is central, so I can pass it on the other side of G. And then I end up with F. Here I have the twist, and here I have G. Let's see, where are we? Oh, now I'm going to change my mind and put G all the way on the top and F on the bottom. Let's see. So and now I slide G back on top of F and put things in order. And I'm done. being a map from something to itself, being a module map, means, so if I have an algebra acting on something, and I have an element of the algebra, an action by that element is an algebra homomorphism, that's the same thing as saying that, yeah, the thing is central. So here is the main technical definition that is needed in order to make sense of this quotient category, where so we start with the category of all tilting modules for the quantum group. That category is not semisimple, has infinitely many kinds of objects. We want to make a smaller category that is semisimple and has finitely many kinds of irreducible objects. The way to do it is to keep the same objects, keep the same representations, and mod out the Hom spaces. Hom from V to W, and now I need a new notion of Hom space. And what I'm going to mod out are the negligible modules, and the negligible morphisms. The negligible morphisms are defined by this property of producing always 0 when you quantum trace them against something else. In particular, and here's another definition that goes alongside this one, which is that an object itself is negligible if the identity morphism is negligible in the above sense. So that's first definition, then using that, we have this new definition. So if I take this quotient category, where I start with a category of tilting modules and then redefine the Hom spaces to be the old Hom spaces divided by the negligible morphisms, then I have a new category where negligible objects have now become isomorphic to the 0 object. So what does it mean to be isomorphic? It means that there is a map one way and a map the other way, such that the composites are the identity. Well, okay, so I have the 0 object, I have a non-zero object. Which maps am I going to take? I take the 0 map and the 0 map. Now I need to check that this is an isomorphism in the category. So if I start with the 0 object and I do 0 and then 0, fine, that's an isomorphism. Now I start with this guy, which is not the 0 object, and I do the 0 map and again the 0 map. I have the map 0 from V to itself, and I need to check that that is the identity. Well, let's see if it's the identity in my category. My category has some new notion of Hom spaces where I've modded out by those. So I need to check if the identity map is negligible. Well, by definition, that's exactly what I've imposed. So doing this quotient construction makes all negligible modules isomorphic to the 0 module and effectively gets rid of them. They're still there because the objects haven't changed, but I've changed the morphisms in such a way that if I think purely in terms of category theory, these objects are equivalent to the 0 object. So let me write it down, because that's the main point of all these lectures that I gave, was to construct this category. So let me just say, So the objects are finite dimensional tilting modules for, and now I'm back at the root of unity case because that's the interesting one, UQ res G. So, and Q is a root of unity, so let me write it as Q to the L equals 1 here in the index, where Q is a root of unity, and the morphisms so are given by Hom of UQ res G modules from V to W modulo negligible morphisms. So there's some things that need to be checked to see that this is a category. I mean, you can't just, in principle, take a category and do an arbitrary quotient and expect to have a category. But so what needs to be checked is essentially that if f is negligible and g is arbitrary, that the composite fg is negligible. And the definition is rigged in such a way that that's really what you get. And then which side you put the g on doesn't matter because of this equation. So you have the same condition also on the other side happening. Okay, so I gave you a definition. So that's a fusion category. That, and Chris in the afternoon is going to show that this is actually a modular tensor category. Let me be precise. Q to the L is 1. Actually, maybe I should have written it as Q to the 2L is 1, because I only care about situations where Q is an even, is a root of unity of even order. So, and L needs to further be, let me write it here. L is even if the following occurs in the Lincoln diagram, and L is divisible by 3 if the following occurs in the Lincoln diagram. So if you don't impose these things, the definition still makes sense, but it might fail to be a modular tensor category. Yes?
So what's the precise statement of uniqueness of either mu or nu or the quantum dimension?
I don't think that they're unique.
Oh, so
I don't think that I don't think that nu is unique. I mean, maybe I'm wrong, but I believe that it's genuinely adding extra data. And well, I've just given you some data, and with that data, you can make sense of all that stuff, and then you can ask, is the category modular?
No, but my question was whether or not that category depended on the quantum group or on some extra choice.
Well, it depends on all these choices that I made. It depends on, I mean, I gave you a whole bunch of explicit formulas. Well, that's a definition. And your question is, does it depend on the formulas? And the answer is yes, it depends on the formulas. If I give other formulas, you might get something else.
Well, I mean,
it's a constructive thing.
Yeah, but, I mean, the formulas you gave are just, you constructed the R matrix, fine. Let's give this for granted. Now,
okay.
You've got a braided tensor category. And so the notion of having this quantum dimension, I thought that guy would be unique, which is surprising. So you're killing every module that has quantum dimension 0 in this condition.
Yes, so I believe that the notion of quantum dimension depends on the choice of well, equivalently mu or the twist. Those two things are equivalent. But I think that it's generating extra data, and that you make another choice, you might get some other things. But maybe there just isn't any other choice to be made in that particular example.
Right,
But I don't know. I don't know. I think it's extra stuff. Okay, so a negligible module, well, how am I going to recognize that something is negligible? I want to have a feeling of which things are going to die. Suppose that V is irreducible. So tilting modules are often not irreducible. They're like indecomposable, but they have all these submodules. But let's check the ones that are irreducible. Suppose V is irreducible, then how am I going to check that the identity is negligible? I claim that that is equivalent to just checking that the quantum dimension is 0. Well, because, okay, the identity from V to V, that's this F here, and I need to check it against any other map from V to V. But V is irreducible. There's not so many maps. All maps are just multiples of the identity. So essentially, I'm checking the quantum trace of a multiple of the identity. And the quantum trace of the identity, that's a quantum dimension. So let's compute some quantum dimensions in the case to just get a feeling of which modules are going to survive and which modules are going to die. And the good thing about mu and this definition here is that it doesn't use the R matrix. And therefore, I can do the computation for general case. I don't need to restrict myself to SL2. First of all, the quantum dimension of a module V, well, which is, of course, the same thing as the quantum trace of the identity of V, is also equal to the usual trace of mu sub V, of the element that appears here. I mean, this is, if you just think in terms of the underlying vector spaces that show up in this picture, that's V, that's its dual. That's, again, V with a new algebra with a new module structure, but I don't care about the module structure. I'm just going to take the usual trace of this linear map from V to V. So this is a useful formula for the quantum dimension. That's what we're going to use to compute it in examples. Let's first do the simplest case of SL2. In SL2, the quantum dimension of such a module, well, suppose that I have n of these dots. So the usual dimension is n. I need to look at mu acting on this. I don't have mu anymore. In SL2, mu equals k. So I'm looking at the trace of k acting on this module. K acts by q to the minus 3 here, q to the minus 1, here q to the 1, here q to the 3. Add those numbers, that's a trace. And that's exactly the definition of quantum number n. So the quantum dimension of the n-dimensional representation is quantum, let's see. The quantum dimension of V is quantum the dimension of V. let's see if I can write it in a suggestive way. Q dim V is dim V Q. Oh, just for SL2, yes. Sorry, make sure that you don't think that this is multiplication by Q. This is a single, this is quantum dimension. So that's for SL2. That's the SL2 story. Now I want to do the general case. Oh, no, before I do the general case, I want to have a look at which things have quantum dimension 0. So now suppose that Q to the 2L is equal to 1. That implies that quantum L is equal to 0. So the modules that will survive in this quotient category are going to be, these modules here, that's the module W sub. Well, the module that survive are W0, the one-dimensional module, W1, all the way to W. Let's see. WL minus 1 is of dimension L, and therefore it dies. So WL minus 2, these have non-zero quantum dimension. The W whose highest weight is equal to L minus 1 has quantum dimension 0, and it's still irreducible. So these are all irreducible. In particular, they're all tilting modules. And then the next ones, these are no longer irreducible, in particular, not tilting. So they're not in the category that we're looking at, and we don't look at them. And if you look at the tilting module that has this as highest weight, that tilting module is going to have embedded into it also a copy of this guy. And then if you compute the quantum dimension of that big tilting module, you will get 0. So all these guys, starting from there on, have quantum dimension 0. Except that the computation that I'm about to do only shows it for this guy. So that's the SL2 story. Now I want to do the general story. Let's see.
So it looks to me like if you look at the tilting module for a higher weight, then it'll have a sub-module inside that is of dimension 0. So when you pass to the quotient, you end up having that is isomorphic to one of the few first ones.
So let me redraw one of these pictures of tilting modules.
So there's one at the top that is a submodule and has dimension 0. So you quotient out by that guy, and you're left with someone that was already considered. So this is isomorphic to one of them.
So here in this example, I have L equals 5. And I'm looking at a tilting module that has a filtration. So this is a submodule, which is isomorphic to, it's the Weyl module with highest weight. Well, it's 7-dimensional, and its quantum dimension is going to be quantum 7. So this was quantum dimension here, you can't see that. Quantum 7 is the quantum dimension of that submodule. If I look at the quotient module, which is this, that has a quantum dimension quantum 3. And when q squared is of order 5, then we have 3 plus 7 equals 0. That's just something you can check. So 3 itself is not 0, 7 itself is not 0, but 3 plus 7 is 0. So you have this Weyl module is not part of your category. That Weyl module is part of your category. And the tilting module is part of your category. But the tilting module has quantum dimension 0, and therefore, whenever you see a summand which is that whole thing, you may as well throw it away. That tilting module, actually, I can say something stronger than it having quantum dimension 0. It's negligible, which is a little bit of a stronger statement. So, okay, let's do the general computation to see which things are going to become 0 in this category. So maybe you remember in the very beginning of my lectures, I talked about the Weyl character formula. Well, the reason I talked about it is because now I'm going to use it in order to compute these quantum dimensions and get some actual formulas for them and check if it's 0 or non-zero. So let me recall the Weyl character formula. So the character of a Weyl module is a sum over the Weyl group divided by another sum also over the Weyl group minus 1 to the length of the element of the Weyl group. Before I used an exponential of the form e to the something, but there's no e's in this story. There's lots of q's, so it's going to be convenient to write it as q to the something. So q to the w acting on lambda plus rho, and here w acting on rho. Okay, there's a few other differences between this formula and the one that I showed before. Before, I had a formula that did not involve rho. Indeed, I had not defined rho. But what I had was a shifted action of the Weyl group, where the Weyl group was acting with some shifts. And it turns out that these shifts can be re-expressed in terms of rho. So W acting shifted action on lambda is the usual action on lambda plus rho, all that minus rho. And if you use that, you can sort of go back and forth between these two formulations. So I'm going to use that one. The quantum dimension of W lambda, well, that is the trace on W lambda of this thing here, and that thing is where it was defined by looking at what rho was. It was a monomial in K that came from looking at what rho was. And that turns out to be the same thing as the trace evaluated of where do I have this? Oh, okay. Switch the 2 pages, of course. Let's see. Okay, so I'm using a different notion of character, so let me say what I mean. So before, the character was defined as the character of a module evaluated on an element T, so that I'm just writing the previous definition, sum over all weights on the lattice of a dimension of the weight space at weight lambda, and then e to the mu paired with t. That's the formula I had before. Now I'm going to use a slightly different formula, but which is essentially equivalent, which is to say, well, I don't put e here, but I put q. That's all. That's allowed. And that, now I'm going to think of it as being a function from lambda with values in z adjoin q inverse. That's just a slightly that's just thinking about what kind of values we allow for t. Before, we were allowing all kinds of values that are not necessarily sitting on the lattice, but also sitting in between. Now we're just focusing 2 values on the lattice. And then we know that it lands in here. I mean, if it's not in the lattice, then it's unclear where it lands, because q is just a formal thing. OK, so we have that expression. Sorry, I guess it's not this that lives in here. It's the character of M lives in here. And is given by that formula. And is also given as the trace on M of q to the, well, let me use another letter. Well, I guess it's OK. Well, here I use a letter tau for an element in lambda, and then I can talk about q to the tau, which is, well, I mean, if you unravel what this might possibly mean, it really means that. That's q to the tau is a thing that at a weight mu takes this value. The quantum dimension, I'm going back to this thing, is the trace on w lambda of q to the 2 rho. And that's the same thing as the value of that function at the point 2 rho. OK. So to compute that number, we're going to put it in that formula. And recall that there's also an extra, so when we derive the value character formula, the denominator first came as a product. So there is an auxiliary formula, I think it's called the Weyl denominator formula, that says that this sum, alternating sum over the Weyl group of q to the w acting on rho can be written as a product over positive roots of, and again, it's going to look slightly different from what I had before. Before, I had 1 minus e to the minus alpha, but now I've incorporated this rho shift, and you end up with having something that's not 1 minus q to the some power, but that's more symmetric. It's q to the minus alpha over 2, no, q to the alpha over 2 minus q to the minus alpha over 2. So there's this formula, and there's the same formula where the denominator has been replaced by that. And we've seen both. So we have these formulas, so let's go on. This is equal to sum minus 1 to the w, q to the w acting on lambda plus rho, paired with 2 rho, divided by sum minus 1 to the w, w acting on rho, paired with 2 rho. Now we're going to use this denominator formula to replace the denominator by a product. And also there's a surprise, which is that the numerator, which a priori you don't expect to be able to write it as a product, because of the fact that I can put this 2 rho on this side, this is symmetric in this and that, I can reinterpret it as, well, so this is also, so this is the Weyl numerator for this highest weight evaluated at 2 rho, but it's also the Weyl numerator for this highest weight evaluated at that point. And that's the Weyl denominator. So you can rewrite it as a product on both sides using this. And you end up with product alpha over the positive roots. Here also, and we have q to the alpha lambda plus rho minus q to the minus alpha lambda plus rho. And here we have q alpha rho minus q to the minus alpha rho. And this factor of 1/2 got eaten in the fact that here we had 2 rho. And if I take each one of these pieces and divide it by the quantity q minus q inverse, I can rewrite it as in terms of quantum numbers. So recall that quantum n is q to the n minus q to the minus n divided by q minus q inverse. Well, I can put that in here to rewrite it as a single product of quotients of this inner product, lambda plus rho, quantum number, whatever that inner product is, divided by that. So here I've computed some quantum dimensions. This is called the quantum dimension formula. Note something interesting, which is that if you set q equals to 1, you get a formula for the actual dimension of the representation. And if you wanted to compute the actual dimension of the representation starting from the Weyl character formula, you can't really. I mean, it's the value of the character at the point 0, but if you put in 0 instead of lambda, you end up with 0 over 0. So the one place where the Weyl character formula fails to provide an answer is to compute the dimension of this. However, if you don't want to compute the dimension, but the quantum dimension, then you can do it. And at the end of the day, you can set q equal to 1 and get a formula for the dimension. So this is a sort of cool little application of that, where you sort of get a formula that you expected not to be there. Good, we have that formula. So now let's see which W lambdas, which Weyl modules are going to be negligible. Well, that's when this quantity becomes 0. In other words, when this numerator becomes 0. The numerator becomes 0 when this thing inside is exactly the order of q squared. So this is 0. When L divides one of those things, when there exists an alpha positive root such that L divides that quantity. And let's think about when does that happen? So I will draw a picture in type A2. So here is the weight lattice. And let's take an example. L equals haven't really, well, I haven't prepared that, so I'm not exactly sure what L is. But I will tell you when this quantity becomes 0 for one of the, when this numerator becomes 0. So it becomes 0. So here is when the numerator becomes 0. And then there's other places where the numerator is 0. Here. And then continues. So you have, so this is when, well, we can compute what the thing is. So this is the highest root. So this is one of the roots are here. That's a root, that's a root, that's a root, that's a root. So the inner product with this highest root is equal to 1 on this plane, 2 on this, 3 on that. So the inner product is equal to 3. So that's a case where alpha paired with, oh, I don't need to take lambda, I need to take lambda plus rho. So rho in this case is this. So I believe, oh, I can't do it. Sorry? What is 6? L is 6. Wonderful. Thank you, Chris. So here's the story. Those modules that are in here, so the Weyl modules whose highest weights are in this curvy line. Sorry?
We counted L minus 1 modules in the category, or we counted L minus 2.
The number of modules here is 6, but it grows in a quadratic way in L. So L says how far this wall shows up. So these are the modules that survive. Those modules are still irreducible. The Weyl modules for these highest weights are still irreducible, but their quantum dimension is 0, and they become negligible and become equivalent to the 0 object in the quotient category. And then those guys here are, the Weyl module is not irreducible, and the corresponding tilting module is going to contain, for example, the tilting module for this guy is going to contain a sub-Weyl module for this guy. And the formulas for the quantum dimensions give that this is, the quantum dimension for this and for that are minus each other, and then we end up having a total quantum dimension of 0. So all the tilting modules having highest weight above all produce 0. They all go away, and the category is now a category which is semi-simple with finitely many simple objects. And then one has to check that it's a modular tensor category. That's another substantial piece of work. If you do that, then you can take that category as the input of the construction described in Chris's talks to then go on and produce all these three-manifold invariants at the end of the day. Okay, well, thanks a lot.